In this session, we will see what are inflection points of a curve. You observe this curve. On the interval AC, the part of the curve is concave upward. On the interval CB, the part of the curve is concave downward. That is, this is the point where the graph changes its concavity. That is, it changes from concave upward to concave downward. Similarly, if you take another type of curve like this, there is a point here, say C. The curve changes its concavity, that is concave downward to concave upward. This type of points where the curve changes its concavity is called point of inflection. Now we'll define what is a point of inflection of a curve y is equal to f of x. Suppose f is a continuous function defined on an interval I. The graph of f has tangent at a point C. Then this point C is said to be a point of inflection if the curve changes its concavity, concave upward to concave downward, or concave downward to concave upward. So what is an inflection point? The inflection point is a point on the curve where the curve changes from concave upward to concave downward. That is concave to convex. If it is concave, this can be considered as convex, and vice versa, or vice versa. Now some more fact about the point of inflection. You just observe this curve. You can see that this is a point of inflection where the curve changes from concave downward to concave upward. And you observe the tangent drawn at this point. This tangent drawn to the left portion of the curve, and this is a tangent drawn to the right curve at the point P. This curve seems to be crossing the tangent. Similarly, this is also a point of inflection of this curve because it changes from concave upward to concave downward. See that the tangent at this point is such that the curve is crossing the tangent. Similarly here, this point is a point of inflection of the curve which changes from concave upward to concave downward, and here also the curve crosses the tangent. So whenever tangent exists at the point of inflection, the curve crosses the tangent. That's the peculiarity of point of inflection. Now how do we determine the point of inflection? Suppose C is a point of inflection of the curve. Now, and assume that the curve changes from concave upward to concave downward. We know if in an interval, say AC, the curve is concave upward, its second derivative f double dash x is greater than 0. Similarly, if the curve is concave downward in an interval CB, there f double dash x is less than 0. So in the interval AC, f double dash x is greater than 0, and in the interval CB, f double dash x is less than 0. And therefore at the point C, what happens to this f double dash x? Either f double dash x exists, or if f double dash x may not exist sometimes. If f double dash x exists, what is f double dash of C? At the point x is equal to C. What is f double dash of C? To the left of C, f double dash x is positive. To the right of C, f double dash x is negative. So at the point f double dash of C must be 0. F double dash is 0. And with the property that to the left of C, f double dash x C and is positive. To the right of C, f double dash x is negative. If the curve is like this and C is a point of inflection, here also you can see f double dash of x is negative to the left of C and is positive to the right of C. That means f double dash x are opposite in sign when x changes or when x crosses C. When x is crossing this C, f double dash x are opposite in sign. And f double dash C is equal to 0 if derivative exists. If derivative f double dash exists, then f double dash c is equal to 0 at the point of inflection. And to the left of c and to the right of c, observe f double dash x, they are in opposite sign. So this is the condition required for inflection point. How do we identify inflection point C if a function is given? Suppose y is equal to fx is given, then how do we get to the inflection points? First, you identify the numbers where f double dash x is equal to 0 or f double dash x does not exist. Suppose C is such a point, f double dash c equal to 0 or f double dash c does not exist, then C is likely to be an inflection point. If the second condition is also satisfied, we can make sure that C is an inflection. First, so what is the second condition? To the left of C and to the right of C, if you calculate for x here, if you calculate f double dash of x, if f double dash of x1 and f double dash of x2, where x1 and x2 are opposite on either side of C, are opposite in sign, then clearly the curve changes its concavity, and therefore C can be taken as an inflection point. So what are the things to be remembered for finding the inflection points? First, for the function y is equal to fx, you find f double dash x. Find out the points where f double dash x is equal to 0 or f double dash x does not exist. These points are really the candidates for the inflection points. That means they are likely to be the inflection points. The next thing is, you find, if C is such a point, you find f double dash x to the left of C and to the right of C. Suppose C is such a point, you take x1 and x2 here, find f double dash of x1 and find f double dash of x2. If they are of opposite in sign, then make sure that this C is an inflection point. Now let us take a problem. Here we have to find the inflection point of the function fx is equal to x raised to 4 minus 4x cubed plus 12. So as we discussed, the given function is fx is equal to x raised to 4 minus 4x cubed plus 12. You find the first derivative and the second derivative. You can see that the second derivative f double dash x is equal to 12x into x minus 2, which exists for all x. So there is no point where f double dash x does not exist. Now get f double dash x, the point x where f double dash x is equal to 0. So f double dash x is equal to 0 implies 12x into x minus 2 equal to 0, which implies we are getting x is equal to 0 and x is equal to 0. So x equal to 0, x equal to 2 are the 2 points likely to be the points of inflection. Now this is the graph of the function. Even otherwise, we can check whether 0 is an inflection point or 2 is an inflection point. So this is the point at x is equal to 0, which is 0, 12. Y coordinate is 12 here. If you calculate when x is equal to 0, we are getting 12. So 0, 12 is a point. Here we are getting another point we have got is 2 minus 4. Now we have to identify, we have to assure this 0, 12 is an inflection point. For that, you find f double dash of x around the point 0. You take a point here to the left of 0, to the right of, or you can take minus 1 and plus 1 for convenience. You find the f double dash of minus 1. Similarly, f double dash of 1 to the left and right of 0. The 0 is the point we have to determine whether it is inflection point. You take minus 1 and plus 1 on either sides, calculate f double dash of minus 1 and f double dash of 1. So what is f double dash of minus 1? F double dash is 12x into x minus 2. So 12 into minus 1 into minus 1 minus 2. So this is a negative number, this is a negative number which is clearly greater than 0. And f double dash of 1 is equal to 12 into 1 minus 2. This is 1 minus 2 is negative, so this is negative. That means f double dash of minus 1 and f double dash of 1 are opposite in sign. Then we can make sure that 0, 12 is an inflection point. And from the graph also we will get the same thing. To the left of 0, you can see that it is concave upward, and to the right of 0, it is concave downward. And therefore, at 0, the curve changes its concavity, and 0, 12 is a point of inflection. Now, what about 2 minus 4? Look to the left of 2, to the right of 2, you calculate f double dash 2 there. F double dash at calculate f double dash of 1. Of course, 1 is left of 2. and f double dash of 1 we already calculated, which is less than 0. And now you calculate f double dash of 3, for example, to the right of 2. F double dash of 3 is equal to 12 into 3 into 3 minus 2, which is clearly greater than 0, so positive. That means f double dash of 1 and f double dash of 3 are opposite in sign, and therefore the point 2 minus 4, 2 minus 4 is a point of inflection. Even from the graph also you will get the same thing, because to the right it is concave upward, to the left it is concave downward. So at this point the curve changes its concavity, and hence 2 minus 4 is the point of inflection. So this is how do we find the points of inflection. First identify the points where f double dash x equal to 0 or f double dash x does not exist. Here in this problem we have got 2 points, 0 and 2. Now after getting the points 0, 2, you evaluate f double dash of x on either, taking points on either side of 0 and similarly on either side of 2. This way we can assure that the 0 and 2 are inflection points or not. Now take another problem. Find the points of inflection of fx is equal to x minus 1 raised to 1 by 3. The same way you identify the points where f dash x does not, f double dash x does not exist, or f double dash x equal to 0. Here fx is x minus 1 raised to 1 by 3. F dash x is 1 by 3 into x minus 1 raised to minus 2 by 3. F double dash x is 2 divided by 9 into x minus 1 raised to 5 by 3. Now observe that this f2x does not exist at x is equal to 1. F double dash x is a continuous function except at x is equal to 1, and f double dash 1 does not exist. And f double dash of x is not becoming 0 anywhere in R, and therefore 1 is the only such point where either f dash x is equal to 0 or f dash x does not exist. So f double dash 1 does not exist here. Corresponding to x is equal to 1, y coordinate is f of 1, which is 0, 1, 0. So 1, 0 is likely the point of inflection. So this is a point 1, 0. This is likely to be the point of inflection. Looking at the graph, if you draw the graph, then we can see that the curve changes its concavity from concave upward to concave downward, and therefore 1, 0 must be a point of inflection. Even otherwise, you calculate taking values left and right of 1, say for example 0 and 2. This is to the right left of 0. You calculate f double dash of 0 and similarly f double dash of 2. You can see that they will be opposite in sign, and hence we can make sure that this 0.10 is also a point of inflection. So this curve is having only one point of inflection, which is 1, 0. F double dash changes the sign from positive to negative, and therefore 1, 0 is a point of inflection. And another fact you should understand that we got that the point of inflections are occurring at x where f double dash of x equal to 0, or if x is a point of inflection, then f double dash x will be 0, or f double dash x does not exist. So these are the one of the conditions required. Either f double dash x equal to 0 or f double dash x is not equal to. So this is actually a necessary condition. That is, if x is a point of inflection, then f double dash x will be 0, or f double dash x does not exist. What about its converse? Can you make sure that suppose f double dash x equal to 0, can you say that it is a point of inflection? Need not be. That is, this result is telling. The numbers where f double dash x equal to 0 or f double dash is discontinuous is not a guarantee for point of inflection. It only gives candidates for inflection points, or they are likely to be points of inflection. For that, let us consider a function like fx is equal to x raised to 4. If you calculate this, a graph of the function of x equal to x raised to 4. Now find f double dash of x. You can see that it is 12x square, 4x cube, 12x square. Equal to 0 implies you are getting x is equal to 0. So clearly 0 is likely to be an inflection point. But what about the nature of the graph around 0? We can see that to the left of 0 the curve is concave upward, to the right of 0 also the concave upward, So the curve is not changing its concavity. And to test analytically, you take 2 points -1 and +1 on either side of 0 and calculate f double dash of -1. Similarly, f double dash of 1. You can see that they are of the same sign. Here it is positive. This is greater than 0. This is also greater than 0. And therefore, this point 0 is not a point of inflection of the curve fx equal x raised to 4, even though f double dash 0 equal to 0. Similarly, take the function gx equal x raised to 2 by 3. Here, this is the graph of the function gx is equal to x raised to 2 by 3. And you can see that this is the point where this function is not differentiable. Here, f is not differentiable and f double dash of 0 also does not exist. Second derivative also does not exist. F double dash 0 does not exist. So, 0 is a point likely to be a point of inflection. Now we have to find f double dash of some -1 and f double dash of +1 on either side of 0. You can see that they are opposite in sign. From the graph, you can see it is looking concave downward, it is concave downward. On the right side also, it is concave downward. So there is no change of concavity around the point 0. Therefore, 0 cannot be a point of inflection. So this result says that even if f double dash x is equal to 0 or f double dash does not exist at some point C, then C is only likely to be a point of inflection, not always. So this is an example, fx equal x raised to 4. Similarly, gx is equal to x raised to by 3 are the functions having no point of inflection. Their derivative becomes 0, second derivative becomes 0, and in the second case, second derivative does not exist. Now take a practical problem. It is concerned with the dive of a submarine. The depth at time of the prototype of a twin piloted submarine is given by ht is equal to tq into t minus 7 raised to 4 in the interval 0 to 7. You have to find the point of inflection and interpret this result. So there is a question here. So you have to identify the point of inflection. The given function is ht is equal to tq into t minus 7 raised to 4. Find the derivative h dash t, h double dash t you find, and see when h double dash t equal to 0. You can see that h double dash t equal to 0 when t equal to 0, t equal to 7, and another quadratic expression t square minus 60 plus 7 equal to 0, which gives t equal to 3 plus or minus 2. So that means we are getting 4 points where derivative, second derivative is equal to 0. One is 0, 7, 3 minus root 2, and 3 plus root 2 are the points. Clearly, 3 minus root 2 and 3 plus 2 are the interior points. 0 and 7 cannot be the point of inflection because to the left of 0 there is no part of the curve. To the right of 7 also there is no part of the curve. So we cannot identify whether it changes from negative to second derivative. The curve changes from concavity to convexity like that. So 3 minus root 2, 3 plus root 2 are the 2 points likely to be the points of inflection. Now you calculate f double dash of x to the left of 3 minus root 2 and to the right of 3 plus. You can see that similarly to the left of 3 plus 2 root 2 and the right of 3 plus root 2. You can see that f double dash changes from positive to negative when it crosses 3 minus root 2 and changes from negative to positive when it crosses 3 plus root 2, and therefore 3 minus root 2 and 3 plus root 2 are the inflection points of the curve y is equal to tq minus t minus 7 the whole raised to 4. So what is the importance of these points? That is interpreted this way. The graph of which you can see that it is concave upward in the interval 0, 3 minus root 2. Hence the submarine is accelerating downward. This is the downward part of the sea. This is the sea. This is the sky part. The sea is shown above here. This is the depth of the submarine. Submarine goes like this through the sea. So in the interval 0, 3 minus root 2, the curve is concave upward. The meaning is the submarine is accelerating downward to the depth of this height, which is approximately h of 3 minus root 2, 3427 over the interval 0, 3 minus. From there onwards, 3 minus root 2 to 3 plus root 2, actually it is concave downwards. So what is happening to the submarine? In the interval, the submarine is decelerating instead of accelerating. It is decelerating. And it reaches its minimum depth, maximum depth here. Maximum depth is here, and it is coming to this place. So from t equal to 3 minus root 2 3 plus 2, it is such that the submarine is decelerating downward from 3 minus root 2 to its lowest point, then decelerating upward. Decelerating is coming upward, coming to the sea level of the water. So it is decelerating upward until t is equal to 3 plus root 2. From 3 plus root 2 to 7, what is happening? The submarine decelerates upward until it reaches the surface. That is 7 minutes after the start of the test dive. Now, the rate of descent of the submarine is greatest at 3 minus root 2. Here it is descending. So the rate of descent of the submarine is greatest at 3 minus. Similarly, the rate of descent at 3 plus root 2 is the largest, is the maximum. That means the rate of ascent, here it is ascending. So rate of ascent is the greatest at 3 plus root 2. Here the rate of descent is greatest at 3 minus root. So these 2 points are important as far as this problem is concerned. As far as the submarine is concerned, these points of inflection are the points where it has got maximum acceleration. That is, whether it is ascending, when it is ascending, when it is descending, when it is ascending also. This is the point where it has got more acceleration. So with this, I conclude the session. Next session, we will be seeing with another different concept. Thank you.